All right, if I could take a minute to go over what we've learned this week, right? Let me actually, I can pull out my notes real quick. What we learned this week is we learned that we're talking about electrostatics, which is the study of charges that are mostly stationary. That a charge is a fundamental property of matter that allows the matter, to experience an electrostatic force, and that these are governed by Coulomb's law. And then yesterday you would have done those stations where you got to see like how you can charge things with friction. You saw how like charges repel, opposite charges attract. You saw that if you built up enough charge, enough positive and negative charges, like for example on the Wimhurst machine or the Van de Graaff generator, that you could get the charges to actually jump through the air and make a spark. You found that the charges, if we think about the atomic model of what charges are, that it's the positive charges that are stationary, the negative charges that move. But we also talked about in class on either Tuesday or Wednesday, we talked about how, even though that's what happens, sometimes we talk about it in the conventional model as if both the positives and negatives can move. We just know that in reality, positive charges stay stationary, negative charges move. But today I want to focus more on the Coulomb's law. So it was given to you in the notes after your test earlier this week. Again, there was a station about it yesterday. But if you'll notice, we have a problem here because this equation only deals with two charges at a time. And so the question that I want to talk about today is what is it if there's more than two charges? What do you do if you have more than two charges? So if you've got more than two charges, you can't actually, you can't just multiply Q1, Q2, Q3. That doesn't work. You've got to kind of consider each pair of charges separately and superimpose them on each other. We've used that word superposition before when we were talking about waves, right? We talked about if you had two objects or two waves that were trying to occupy the same location, they can superimpose on each other. It's the same thing with charges. If you have two, if you have one charge that's being affected by two other charges, the effect of each of those charges is superimposed on each other. And so I want to do a practice problem today where we look at more than two charges and see if we can figure out what the total force is on a third charge. So here's the problem. 3-point charges, Q1, Q2, and Q3 lie along the x-axis. And I'm just going to label this on my picture here so that it's easier to see in a second. At x equal negative 0.4 meters, x equals 0 meters, and x equals 1 meter. Calculate the magnitude and direction of the electrostatic force on Q3, on this charge. And then it tells us how big each of those charges are in coulombs. All right, so let's look at this. So the first thing that I do when I give one of these equations is I kind of try to label my picture, as I've already started to do here, but I want to label a little bit more here. I want to point out, you'll notice that Q1 here has a positive charge, and the other two are negative charges. That's going to be important in a second, so I'm going to label those so that I can look at them here in a little bit. And as we said, this equation, the Coulomb's law equation, only works for two charges at a time. So the way that I usually do this is I figure out how many pairs of two charges there are. And there should be, I think, 3 pairs here, right? You have 1 and 2 is a pair, 1 and 3 is a pair, 2 and 3 are a pair. And to keep things simple, I usually start by calculating the absolute value of the 3 pairs of forces first, and you'll see why I'm doing that in a second. So I want to find 2 things. I want to find 3 things. Find the absolute value of the force between charge 1 and charge 2. Find the absolute value of the force between charge 2 and charge 3, and the absolute value of the force between 1 and 3. So those are the only 3 pairs of charges we have. We've got these 2, these 2, these 2. All right. So the way we do this, right, so this equation works for 2 of the charges at a time, so I'm going to just fill this in. So this would be K, Q1, Q2, divided by R squared. And this R, what I'm talking about is the R between 1 and 2. Charge between 2 and 3, I would call F, Q2, Q3, not F, sorry, K, Q2, Q3, over the separation between charges 2 and 3 squared, and then K1, K, Q1, Q3, divided by the separation between 1 and 3 squared. And I'm calculating the absolute value, so I'm going to, for the time being, ignore the fact that some of these charges are positive and negative. We're going to come back to that in a second, but I find it easier to ignore it at this step in the problem. All right, so we know what K is. So for each of these, we're going to have 9 times 10 to the 9th is what K is. I'm going to drop my units just to be a little more compact. So Q1 is 1.3 times 10 to the negative 5. I'm going to zoom in on this one so you can see it. Q2, if we look up here, Q2 is 6.0. Again, I'm ignoring the negative, times 10 to the negative 5. And then the separation between 1 and 2 looks to me to be 0.4 meters. 0.4, so just 0.4 squared. So 9 times 10 to the 9th. Let me see if I can make it so it's easier for you to see. 9 times 10 to the 9th times 1.3 10 to the negative 5th times 6.0 times 10 to the negative 5th divided by 0.4 squared is 43.875 newtons. Now I'm going to give you a minute to find the other two. So Mrs. Taylor, if you could just pause this video for a second. Give everyone a chance to solve these other two. So you can take a minute here to check your answers. So the force between 2 and 3 should be 30.78. The force between 1 and 3 should be 3.40. Now one thing, if you didn't get particularly this last one thing to point out here is make sure that for your radius, your separation between 1 and 3, the separation between Q1 over here, the separation between Q1 over here and Q3 over here is a full 1.4. Right, so make sure that's what you've got there. So now we've got each of the three forces. And now what we're going to do is we're going to combine them to figure out what the force on Q3 is. So I'm going to just redraw, well, let me think about how I want to do this here. So what I want to do, I'm going to draw the free body diagram here for Q3. So right here, down here, I'm going to draw the free body diagram for Q3. And the idea is we need to think about which forces are acting on Q3. And there are two of them. There are two forces acting on Q3. There are these two. This one doesn't act on Q3 because that's only acting on 1 and 2. But let's think about what each force is doing. So the force between 2 and 3, if you look at your diagram, the force between 2 and 3 are both negative. Like charges repel. That means that these things are going to go in opposite directions, right? Now, you got to ask yourself, what is happening to, which way is Q3 going? Q3 is not going to the left. Q3 is going to the right. So when I draw this diagram here, when I draw my free body diagram, I'm going to say that the force between 2 and 3 is pushing 3 to the right in the positive direction. What is the force between 1 and 3 doing? So I'm going to erase this so we don't get confused. What is the force between 1 and 3 doing? Well, 1 and 3 are positive and negative. They're unlike charges, so they're attracting. So which way is 3 going? 3 is going left. So the force between 1 and 3 is that. So if I want to then find the net force acting on charge 3, what we're doing is we need to add the force between 2 and 3 because it's going in the positive direction. And we need to subtract the force between 1 and 3, because it's going in the opposite direction. It's going backwards. So the force between 3 then is going to be 30.78 minus 3.40, which I'm getting to be 27.38 newtons. And to be kind of complete, I would say it's because it's positive, it's pushing it to the right. Now, while we're at it, just to make sure that you understand this, I would like you to try to find the net force on 2 and the net force on 1. So I want you to see if you can find these two as well. We've kind of already done most of the number crunching, but basically what I need you to do is I need you to draw 2 more free body diagrams and see what happens. So I'm going to have Mrs. Taylor pause it again for a minute, give you a few minutes to attempt that on your own. And then if we take a look here, let's draw our free body diagram 2. I just want to make sure that everyone has this right. So if you look at 2, the 2 forces that act on 2 are these. Now this is going to come out a little bit differently than it did the last time because, so let's look, the force between 1 and 2. What is the force between 1 and 2? Well, positive and negative are opposites, so say attract. So it's going to pull Q2 to the left. So the force between 1 and 2 pulls this way. Right? Could you see? I didn't actually look whether I had that in the screen when I was describing it. So let me try again. So positive and negative are opposites, so they attract. Since they attract, the negative one moves to the left. That's why I'm saying that the force between 1 and 2 is to the left. Now let's look at what force 2-3 is doing. Well, if you look at these two, it's interesting because these two are like, so they're repelling. So this is also pushing Q2 to the left. So this time, both forces point to the left. So what I'd say now is that the net force is negative the force between 1 and 2 minus the force between 2 and 3. They're both going in the negative direction. So it's going to be negative 43.875 minus 30.78, which I'm getting to be about negative 74.655 or 66, I guess. So I would say, what does that mean? That means that the net force is 74.66 newtons left. All right, and then let's do this last one here. So if you look at this last one, let's look about which forces are acting on Q1. So I'm going to draw my free body diagram here for Q1. So F12 is pulling Q1. They're attractive. So it's pulling Q1 to the right. So F12 points this way. Let's look at F13. F13, also attractive, pulling Q1 to the right. So F23 goes to the right. So I would have 43.875 plus 30.78. And this is, since it's positive, it's going to the right. I did something wrong. Something's not right. Something's not right. What did I do wrong? F12. Sorry, it shouldn't be F12 and F23. It should be F12 and F13. Sorry, this is not correct. 13. F13 was 3.40. So this is what? 40. How about 47.28? All right. I'm leaving this this answer key with Mrs. Taylor. If you need to take a look at it, pardon me, need to take a look at it to figure out anything that you've missed, I encourage you to talk to your classmates to make sure that you understand this. For the rest of the time here, you can now, I've said you can do this for a few days now, but now in particular, we've really covered everything about Coulomb's law that we need to cover. So on your syllabus, you can work on the first stamp about Coulomb's law. So that's what I want you to be working on the rest of the class today. And I will see you on Monday. For those of you who celebrate, I wish you a happy Easter this weekend. And for those of you who don't celebrate Easter, still I wish you a happy weekend. So I will see you on Monday.